I am DJ Leto here with Sunrise Angels, and now we have Joshua Alan Sturgill here on the phone line to talk about the Vernal Equinox. So I'll give an introduction. He's a bookseller of Eighth Day Books, a poet, and a classical geometry, classical astronomy, and Renaissance literature teacher out of Wichita, Kansas. But I know him from taking an online course he just offered called The Art of Imitating Heaven, the Structure and Meaning in Ancient Cosmology, which was on the Symbolic World online platform. So I think you will be live now, Joshua. You want to say hello?
Good morning.
Oh, good morning. Yeah, we hear you.
Great.
Yeah, thanks so much for coming on the show.
Yeah, you're welcome. This is pretty interesting for me.
Yeah, it's super cool. I really enjoyed taking your online course. It gave me lots of threads to go down. But it was especially interesting when we were looking at the practical stargazing models and sort of the charts and graphs of the rotations of the planets and the sun and the equator, which is hard to represent over the air, but I definitely recommend people to look it up. So I figured we could start with just asking, like, what is the vernal equinox? Just like the literal definition.
Well, the vernal equinox, as the word suggests in its Latin roots, equinox, equal night, is the unique time that happens twice a year, once in the spring, once in the fall, when the amount of time in dark and the amount of time in light is equal. So happens all over the world. If you're on the equator, it's the twice a year when the sun passes directly overhead. Of course, at the equator, the sun moves back and forth above you. Here in the northern hemisphere, then we see the sun rise in the middle of its possible most northern and most southern risings. So it's a unique moment for all cultures, all times and place, because it's an astronomical event by which you can calculate time. You can give number to time by seeing that night and day are balanced at this moment.
Yeah, right. So cultures all over the world observed this going back very far. It's all over the world. The cultures observed that the times of equal day and equal night, and they use it to mark the beginning of the seasons, right? I mean, the beginning of spring.
Yeah. Yes. Yeah. If you live in the modern world, you're always telling time by the clock or by a calendar. And in the ancient world, the sky was your clock. And so when you reached the period of equal day and night, you knew that the days were going to be longer and the seasons were going to be warmer. It was time to start planting. And so we might look on the calendar and say, oh, it's Saturday, it's the weekend. My schedule is going to change. I'm going to do different things other than my job. But in the ancient world, if you were tied to agriculture, you would think, okay, now the clock, the calendar is saying it's time to start planting. It's time to start preparing for the long days, which would mean the stress of winter is officially over.
Yeah, that's really interesting. That's instead of a mechanical clock, it's like a cosmic clock that everyone was following, and they weren't looking at their watches or their calendars on paper. It was looking at the sky to know where you were in the year and the seasons. Yeah, that's really fascinating. And also, I think another occasion with the vernal equinox is a meeting of the ecliptic and the equator, right? There's like the path of the ecliptic and the Earth's equator,
Yes.
and it meets twice a year. And that the mismatch between those two paths is what creates the seasons, right? Because the Earth is tilted on its axis.
Exactly. Yeah. So if you're listeners don't know, the ecliptic is it's kind of the average path of the sun. And in modern terms, we would say the plane of the solar system. When we look up at the sky, we're looking kind of through the plane of the solar system. And that line that the sun and the planets follow, where all the eclipses happen, is the ecliptic. And you're right. Twice a year, as that line, from our perspective, moves back and forth across the sky. If you're on the equator, this is the day when it passes directly overhead and then starts moving on its way north.
Mm. And that ecliptic is also like the backdrop of the ecliptic is the zodiac constellations, right?
Yes, yeah. So exactly. See, you've got all the terminology down. This is very exciting for me.
Oh, great.
I feel like I'm back in school teaching my kids. I'm like, yes, you did it.
Oh, thank you. Yeah, I mean, I learned from you. So what I find interesting about this, the ancient people were observing the equinoxes and seeing this phenomenon, and it seems like they sort of realized this tilt on its axis. You know, I don't think they had an image of the Earth as like a big orb being tilted, but they could tell there was some sort of mismatch there between those two different paths of the ecliptic and the Earth's spin, like some sort of deviation that gave rise to the beginning of seasons. Am I correct with that?
Yes, yeah. In an ancient, more what we now call a geocentric model, it was this interplay between the stars being constant and the ecliptic moving back and forth that would have been obvious, maybe even more obvious to ancient people, that the seasons, warming and cooling, rainfall patterns were all tied to this movement of the ecliptic back and forth.
Yeah, and
besides the fact that you just have longer days.
And so, yeah, they must have observed, so they have their lived experiences, having a summer of like life and planting and harvesting, and then a winter or fall into winter of like decay and death, but also going into rebirth in the spring. So they have this lived experience and like the weather patterns changing, but they're also looking at the stars and observing how that aligns with this sort of the paths of the ecliptic and like where the sun is and the planets relative to the fixed stars changing over the years. So they kind of see a connection there.
Yes.
Yeah. Where I think is really, I think it's fascinating that they were able to make this connection in the first place. It seems like you could call astronomy really like the first science in a sense, because it seems to be the first place that we know of where humans were finding order and being able to like calculate what's going to happen, and whereas like their lived environment was sort of just chaotic. You're just dealing with all the stresses of living, but being able to look to the heavens and see order, and then like orienting yourself with that, it's like the most ancient science.
That's well put. Any ancient site that we look at, say, there's a whole branch of astronomy called Archaeoastronomy, which is looking at ancient sites like the pyramids or Mesoamerican places, or anywhere that you go in the world and you look at ancient buildings. One aspect that's always important to discover is what is the orientation of this structure, this temple or this city. What's its orientation toward astronomical events? Does it face due east on the vernal equinox, like things like Stonehenge? And what was the significance of that for the people living there to be able to tell time, and then, like you said, view the order of the heavens, and then apply that to the chaos, not even in a negative sense, just the possibility or the mutability of Earth. Take what you see as something permanent and then mimic it in your own surroundings, in your environment. It's important to every culture.
sort of building like a microcosm of the macrocosm. So they're taking their cosmological order and then representing it in a sort of monument, a building, or a temple, sort of like instantiating that cosmos as a location and a building that they can go to on Earth, but is really a representation of the cosmos, the universe as a whole.
Exactly.
So you said, so is there a connection between the vernal equinox and the Stonehenge?
Yes. In fact, there's often big gatherings of people. There are several sites in the British Isles, still well-known ancient tomb structures. There's a lot of these ancient sites we're not exactly sure what they were, but artificial hills with a tunnel entrance, and many of those are aligned so that the sunrise on the vernal equinox will shine into that tunnel and illumine an altar or some kind of a stone, perhaps with writings, petroglyphs on it. The back, there's just one day a year, or maybe twice a year if it's aligned with the vernal and autumnal equinoxes, where light will shine and fill the space with light. And so that happened in the ancient world, sites that are we can still visit, but also into the Christian era and even till today, buildings are built with this idea of a beautiful kind of interplay of light. Many Christian churches are aligned, especially if they were named for a saint whose feast day was in the spring. You could align your church so that light shines into the building, perhaps through a stained glass window, through a door. It would come in its farthest approach on that saint's day. So we think, well, that's got to take a lot of engineering, which it really did. It took an incredible amount of precision and communal intelligence and memory being passed through the years of calculating the right day and then building a structure that would capture that astronomical moment.
Yeah, that's amazing. I mean, that really shows like sustained observation over time and like preservation of that knowledge and being passed on, especially if you're talking about like a site like Stonehenge or those mounds you were talking about. It's like I think I see a tendency of like discrediting like ancient people or thinking that they were like just everybody was superstitious or like didn't know anything until science started in like ancient Greece or something. But it's based on these connections to astronomical events. It seems like even in prehistory there was a real like scientific tradition and gaining of knowledge and like preservation and passing it on. I think it's really incredible because that does take. I mean, that sort of some of these observations seems like they can only be done over generations, like especially something like the precession of equinoxes, which is like something that occurs over a 26,000 year cycle, but is like present in ancient myth. Yeah, could you explain the precession of equinoxes?
Yeah, it's more difficult without a visual, but one of the things that we see, you mentioned the zodiac, which are the constellations, the band of constellations, which anciently was divided into 12 parts, through which the sun and the planets are always traveling. So on the vernal equinox, at any time of year, but the vernal equinox is an especially obvious moment of equal day and night. The sun will rise in one of those 12 constellations. But if you've ever spun a coin or used a gyroscope, and you see that there's a moment pretty quickly after you spin it that the axis of the coin or the gyroscope starts to make its own little tiny circle, and the axis starts moving around and pointing different directions. The same kind of thing happens with the Earth's axis over that length of 20-some thousand years, so that at the vernal equinox, very slowly over time, the equinox is happening when the sun is in a different zodiac constellation. And in order to see that very slow progression happening, you have to have some stability in culture and some way to pass knowledge down through many, many, many generations. So I appreciate what you just said. We think about ancient people as having unstable civilizations, being nomadic, being ignorant in one way or another, but they had ways of preserving knowledge of their observations of the heavens over centuries. And they embedded in myth, and they were able to speak mathematically about the precession of the equinoxes, which is this long measure of time, which would have been just as important as the cycles of the moon, for instance, which would be a very short measure of time. And a lot of ancient cultures were interested in harmonizing all of the different time measures given by the planets and then by this precession of the equinoxes as the sun is slowly moving through the zodiac constellations over these thousands of years.
Yeah, they're seeing, the moon cycle is very apparent and regular and a good, the way we measure months, right? But that's something that's more immediately given to people. It's probably sort of relatively easily observed, but then to be able to perceive like things like that precession of equinoxes is like another level, like a lot more
altogether.
Careful. Yeah. But so you're saying they would try to harmonize the two and sort of see how they fit together, like how this like a 28-day cycle fits into this thousands-year long cycle.
Yes, and I think a lot of this we forget is the birth of mathematics. You don't see geometry, for instance. It's this class we have to take in high school, and you have to do these proofs and memorize all the properties of triangles and stars and squares and circles. But for the ancient world, geometry was deeply mysterious, and it was revealed only by observing the heavens. And so all of these different kind of time measurements and the geometry, astronomy, of different philosophical ideas about why these things happen together, all of these science and mathematical disciplines come to us from observing the sky, because they're less apparent, like you mentioned, in the chaos of Earth around us. And so the same principles apply to Earth, but they're clear when we look at the simplicity and regularity of the heavens.
Yeah, it's fascinating that the heavens as a model of regularity and stability and order that inspires scientific development or like mathematical development as tools to describe it and understand it, but when you can also use sort of in our world, almost like gifts from the heavens. I just want to say real quick for our listeners who are just tuning in more recently, we're talking to Joshua Alan Sturgill, who is a poet and a bookseller and a classical geometry, astronomy, and Renaissance literature teacher out of Wichita, Kansas, and recently taught a course on ancient cosmology on the Symbolic World online platform, which I took. But he's on the show today because it is the Vernal Equinox. Just happened yesterday, and I'm doing a Vernal Equinox special, so we're just talking about all sorts of topics related to that. So back to what you were saying about geometry. So you were saying that sort of the development of mathematics, geometry, and things came out from ancient astronomy, like developed from that. Yeah.
Just the observation of the like we'd mentioned, some things like the positions of the stars relative to each other are unchanging, and then the positions of the planets relative to each other and to the stars is constantly in motion, but it's a very regular, predictable motion. And so comparing what doesn't change to what does change is the birth of a mathematical kind of consciousness.
Yeah, I can see that. Oh, go ahead.
Well, I was going to say one of the classes that I teach that I just really enjoy, it never gets old, is Euclidean geometry. And when the opening lines famously of Euclid's geometry text called The Elements is his definition of a point and a line. And he says a point is that which has no part, and a line is that which has length but no breadth and lies evenly on the points upon it. And it seems like two very strange definitions unless Euclid is looking at stars. So the point having no part can mean that it's very small, which is the way we think of it, having no dimension, but it also means can't be divided. So there's no way to divide the point in the same way we would look at stars as being unchanging references for our, mental processes. You would think these points that fill the sky at night are indivisible, do not change, and are the same with their distances relative to each other. So if Euclid is thinking of that as a point, and then he's thinking of the star rising and tracing a path across the sky, he's describing that path as a line. That's the opening of his book, probably the most famous textbook in the world, Euclid's Elements. That's been the basis of Western mathematics for centuries.
Yeah, basically right up until like now, right? I mean, until recently. Yeah, that's so you're saying defining the line by a star moving, but are we talking about like a fixed star? So then you're saying, if you're talking about motion of the star, do you mean like over time moving where it is in the sky? Is that what you meant?
Well, my thought was if you take a star like Sirius, which is the brightest star in the sky, Orion is a very recognizable constellation, even if you're in a city, a lot of bright stars. But just a little below Orion at his feet is the dog star Sirius. If you were to watch Sirius, observe it over several years, you would see it doesn't ever change place in relation to the constellation Orion, but it's bright, it's easy to spot, and you would always see Sirius rising and tracing its path across the sky and then setting in the same place. And I think Euclid had a lot of these ideas in mind when he was thinking about not just what am I seeing, but what is the underlying principle that allows the star to have this appearance and this behavior. It must be something what we would even think of as a philosophical or metaphysical truth behind it, which is the idea that there is such a thing as a point and a line, and therefore planes, parallel lines, and shapes. And he begins with these ideas and then constructs an entire a mathematical discipline, but also just a way to even look at the growth of a tree, which seems very chaotic and complex until you apply geometric principles to it, and you see things like the golden ratio, you see irregularity, you see maybe it puts out two branches every so many years of growth, and you see those branches moving around. You can start applying the geometry of the heavens to things like trees, and suddenly the what wouldn't seem so uniform in the growth of a tree takes on a whole different character and has those same heavenly or geometric principles behind it.
That's fascinating. Yeah, thinking of astronomy, sort of the first science, as being in ancient people, being in like an environment that's sort of chaotic and doesn't seem like there's so much order to it. You're just trying to survive, and you're in nature. But seeing order in the heavens that's very regular, and then being able to observe that motion over time and derive calculations and models for what will happen in the heavens, and predictably being able to predict what will happen there with very, very good accuracy, sort of like being the genesis of this idea of the scientific process in general, of being able to make observations over time and then develop a model and then predict what will happen or understand why something happens, then being able to be applied to Earth. So we get the concept and the process from observing the heavens in a very regular way with regular motion, but then with the knowledge we gain and processes and development of mathematics from that, we can then look at something like a tree and derive understanding of that process as well as the rest of the Earth. And now up until modern day, we have scientific models for, like, well, not all of nature, but a large portion of nature, and like so that whole scientific idea having a genesis with stargazing is really interesting. And just the general idea of just, we can make observations to understand this thing, build a model, and then predict it with good accuracy.
Yeah, and rely on the fact, just to continue what you're saying, rely on the fact that when I make the observation again, it's going to be the same thing. I might make a new discovery, but I won't find that there's something different happening. There's a reliability, there's a predictability on Earth, and I know that that's true because I see that in the sky, in the heaven. And so I can gather scientific data and then trust that it is going to be true over time. We think about that, like you said, as a modern idea, but really it comes to us from the ancient world. And we apply it with technology, with different tools. We apply it to the changing of in matter. We're more interested in how things work rather than why. So those are differences in our modern mentality. But the idea of finding the stable principle and relying on that to then look at things you don't know or that appear unstable, that comes from the ancient world.
Wow. Yeah, that's amazing. Yeah, so we talked about Euclid's Elements. So that was like when was that written? By Euclid, composed by Euclid?
The tradition is that Euclid was one of Plato's disciples, so probably 300 BC, and Euclid was gathering Pythagorean knowledge and kind of systematizing it into a teachable form for Euclid, for Plato's Academy.
So about 300 BC, and then it was, I've heard it called like the standard textbook for geometry. Up until the modern time, so that's roughly like 2,000 years or more. It was the standard geometry textbook that people learned from.
Yeah.
When did we stop using that?
I think in one sense, we've never stopped using it because we go back and refer to Euclid, and a lot of the things he discovered or articulated just haven't changed. Like that the three angles of a triangle will always add up to a straight line. Mm-hmm. That's ancient knowledge. But since we use different measuring systems, you would now learn in school the three angles of a triangle add up to 180 degrees, which is, degrees are an artificial measurement, but it's very handy. Where Euclid would refer triangles to lines, we refer the triangles to a measurement system. So that is a change. There's some different terminology that we use. Plus now, for us, geometry is not the end goal of mathematical education. It's a stepping stone toward algebra and calculus, which historically are just outgrowths of geometry. But we've changed the terminology. We've kind of simplified what Euclid does, and we've broken mathematics, for good and bad reasons, into a lot of different disciplines. So if you're in public schools, of course, you got pre-algebra, algebra, geometry, algebra 2, trig, and then then it kind of, a lot of kids just get burned out, and then some that really love it will go on to calculus. But if you read Euclid's Elements, there's stuff in there we wouldn't consider geometry. There's a whole section in the middle which is number theory. What is number? What are magnitudes and multitudes? He relates the point, that which does not have any dimension, to the Platonic solids, which are the 5 regular polyhedra that can be inscribed in a sphere. And that's his goal in the Elements, and we don't have that goal anymore. We just want, what are the basic principles of geometry? Then we move on to algebra. So I think maybe that's too much explanation, but it's not that we've forgotten all of Euclid. It's just we're not interested in his project. We borrow from him for a different kind of mathematical project today, which is more moving toward engineering and the manipulation of the physical world to meet our needs, rather than the intellectual life and development of a philosophical mentality.
Yeah. For listeners unfamiliar with like the Platonic solids, I think an easy way to understand it is this is 5 3D shapes that basically, if you're familiar with like gaming, like tabletop gaming with dice, those are in the Platonic solid shapes. So you have like a 6-sided die, 4-sided die, a 8 sides, 12 sides, and 20 sides. So those, imagine like the dice from like a D&D session or something. Talking about, if you're talking about the Platonic solids.
Perfect example, yes.
Yeah. And then I do think that we have some exposure to, if I remember like from geometry schooling, it's like we learn Euclidean geometry. That's what it's called. We're learning Euclidean geometry. So we hear Euclid, but that's sort of, I think that's the extent that we really hear about it. And it's similar with Pythagoras. It's like we learn the Pythagorean theorem, and that's like, okay, that's how we know Pythagoras, just going through schooling. Which I just think is interesting that we have their names, we know them from these, but we don't really learn about the people, how they developed it, these concepts, and their own sort of visions or goals. You talked about Euclid's goal being more of you said that the aims of modern geometry education and mathematics are different than Euclid's aims. So what would you consider Euclid's goal with developing his geometric system?
Well, that's a great question. Over the tradition is, and I like it. So I always tell people, I don't know if we know for sure, but over the gate of Plato's Academy was a sign that said, "Let all who are ignorant of geometry not enter here." And so one of the things he was saying was, if you want to train yourself to be a clear thinker, if you want to be a logical, maybe we would say a systematic thinker and a good communicator, then you would start by working through Euclid's geometry, because step by step, beginning with these definitions of point, line, and plane, you end up moving toward proving the truth of the Platonic solids. And along the way, you gather all of these principles of how do you build one idea on top of another in a very stable way. And in the ancient world, of course, they didn't, like, I love being able to go to YouTube and seeing a video presentation of the geometric proofs being worked out. And I encourage my students to do that too, because some of them are very visual. But in the ancient world, you had to like really exercise your imagination. You could draw on the ground, you could draw on a wax tablet, but you had to exercise your imagination to see all of these truths kind of coming alive. And it was exercise not in order to go out and do something. Geometry is very practical, but the idea was you weren't just going out to do something, you were training your soul to imitate the heavens. You were training your soul to be geometric and regular in pursuit of truth, generally speaking, and not just in pursuit of more mathematics.
Like mental, personal, intellectual, mental, and spiritual development being sort of the goal of practicing mathematics.
Absolutely, yeah. For the ancient world, that was the goal of mathematics.
And I think that's the sort of the classical education, of the past, and the movement today sort of is reorienting towards that goal of personal development being the purpose of education, rather than sort of just learning stuff. I don't know, like what would the modern goal be? Like learn this stuff so then you can get answers right and get points, get a job, and maybe contribute to money making somewhere.
Exactly. Yeah. If you are the student, then you want the A. If you're the system, the educational system, you just want people to go out and be able to contribute to the economy. And those are not unworthy goals in kind of in their sphere, but traditionally and classically, education has always been about producing a fully intact human being, someone who can not just have memorized answers, but come up with new questions.
Yeah, and then with geometry Euclid, I think he starts from like there's like 5 or 6 definitions that are sort of self-given, or like you have to start from some basic first principles, but then he develops it through combining these definitions into propositions that then all like compound, sort of being a model of thinking, of being able to rationally think and develop thought towards complex knowledge and reasoning. And also that, that exercise of the imagination, like you said, with the ancient people not being able to, not having YouTube, they had to thinking geometrically, some of these things that really stretches your brain and like makes you have to develop abstract representations in your mind and develop a capacity for thinking. It's almost like molding your brain geometrically, which then imitates the heavens, like you were saying. It's fascinating. And I think that, that concept of personal development being the aim of education, that was in the classical liberal arts, like educations. Well, I think I've heard like Thomas Jefferson was a fan of Euclid's elements. Like a lot of, do you know if that's true?
I've heard similar things.
Like
that it, just as training for logical thought, it can't be beat.
And then that was, right, and that's why it was a piece of the classical liberal arts. But when was this idea of classical liberal arts, right? I mean, before the modern time, including geometry education, when did that really start? Because my impression of that is that it's something that, the average person wasn't really getting that education, but people who had the resources or were maybe higher in society could have this education of liberal arts, and like personal development and philosophical development, sort of like training. But it's not like everybody was getting that, right?
Yeah, and that's a really interesting question, because we often wonder. I think there's a lot of speculation about who was educated and how, in a time when there was less literacy. But literacy, we prize literacy, and we should. But literacy is not necessary to the health and intellectual vitality of a culture. The ability to tell stories, to have an active memory, to have a truth-finding imagination, and a very clear ability to reason. Those things don't depend on being able to read and write. But in the medieval world, there was definitely an educated class that would be connected to the Christian clergy, but also to all of those who showed aptitude. They could be educated with what we now think of it particularly as the Trivium and the Quadrivium. And the Trivium, grammar, logic, rhetoric, is more of a way of teaching where you start with first principles in the grammar stage. How do you add those together in the logic stage? And then how do you articulate them in the rhetoric stage? But then the Quadrivium were these mathematical disciplines, which interestingly would include music, because music is audible geometry. And so you would have had training in arithmetic, very simple, countable math, geometry, astronomy, and then music. And those four things were thought of as all going together. So there would be a lot of general knowledge about those things in society as a whole, because I think those who were educated, part of their job was to go and disseminate that knowledge. But who actually got the education directly is a matter of speculation. And I'm kind of fascinated about it. I'm new to classical education myself, and I'm still doing a lot of research.
Yeah, it's very interesting, and sort of that. I think the aims of the Trivium and Quadrivium learning is akin to Euclid's aims with like the elements, and like Plato's school learning geometry. It's the same idea of that personal, logical, philosophical, moral, and spiritual development. And I just, that sort of attracts me to the idea of education, not for the sake of getting good grades and getting a good job, but education for the sake of higher development as a human being for its own sake is really fascinating. And I've heard the quadrivium described as, they say arithmetic is number, geometry is number in space, music is number in time, and then astronomy being number in time and space. So
I like that. That's beautiful.
Yeah, that's like, so you're getting a holistic conception of number, and it's all, and astronomy is sort of that, like, that climactic moment where everything comes together. And it's fascinating with music, too, being considered as audible geometry, being that it, it works by proportions. Like what sounds harmonious to our ears are certain harmonies and divisions of, string lengths as it was. I think that's how Pythagoras sort of found like harmonic relationships is by dividing a string into certain ratios and observing, like, if you divide a string in half, I think that's an octave.
That's an octave, yes.
Higher.
Well, there's a story that I like, that Pythagoras was walking past a blacksmith shop, and he heard the blacksmith hammering out a sword or some kind of farming implement on the anvils, and Pythagoras heard a perfect fifth and rushed into the blacksmith shop, and then realized that the two anvils were in a certain proportion of 3-2, I think it was. And then, like you mentioned, the proportion of 1-2 would be the octave. And so it's probably an apocryphal story, but it's very illustrative. And then in the Pythagorean school, they would teach this idea with a monochord, which is an instrument with one string. So you can easily see if I divide this string in half, if I press down in the middle and pluck one side, then I've made a sound that is exactly one octave above the sound of the whole string. And then you can do that and divide the string up into these different proportions, and then you'll get all of the basic notes of what we today think of as a 12-note scale with all of the half steps. And there's a lot of changes that happen in the Renaissance and late medieval period with that, but basically that's still how music works. The reason it's pleasing, like you said, is because we are hearing geometric proportion, and it's unfortunate we don't teach that idea of music to everyone today, because I think there'd be a lot more music appreciation, and we would crave better music than we do, I think, if we had a deeper understanding of what music is.
Wow, interesting. Yeah, that's amazing. For those tuning in more recently, I'm talking with Joshua Alan Sturgill. He is a poet and a bookseller and a classical teacher of geometry, astronomy, and Renaissance literature out of Wichita, Kansas. But he taught a course just recently on ancient cosmology on the Symbolic World website. You can find the link for that on WUSB.fm on the playlist for today's show. It's still available as recordings. But the course he taught was on ancient cosmology. But now we're talking about classical education, and it's very, very interesting. Yeah, that's really interesting that, that connection that is then made between geometry and music, this like synthesizing sort of thought that like brings everything together and draws connections and interrelations, rather than having like a separate field, like, okay, here's music class, here's geometry class. Instead, it all builds on each other and connects, and then culminates seemingly like in astronomy, which is like, or like the music of the spheres, or in a sort, which is just like a total cosmological development or like understanding. Is just really interesting. I appreciate the philosophy of this approach, because to me it seems like going through public schooling, it was just like, here's stuff you got to know because we say so, and then here's rules, here's how to apply them, and just do it just cause. And I didn't really have any like why behind anything. It was just like, yeah, here it is. Here's the rules, and here's how to apply them, and then we test how well you can apply them in different scenarios, and then you're on to the next. But I didn't really have any intrinsic motivation towards learning these things, because it didn't feel like there was really any bigger picture. So I wonder, and also, you're in school and you're a kid in school, so you're not always the most motivated anyway.
Yeah.
But
you got other things you're thinking about.
Yeah. So my sort of thought is, well, I do think that this classical education idea, while in the past it was maybe like more an aristocratic experience, I think now in the age of like universal education, it's a perspective and approach that can be brought to everybody. There's no reason for anybody to be limited from having an education in this way, with the current way society is set up. But I just think if you're teaching a student mathematics, and maybe they're coming into your like classical geometry class or something, how do you keep that, like, are you able to like bring that bigger picture into things and keep them interested in that way? I guess I'm wondering about making mathematics, like demonstrating the significance and the importance of these mathematics, not just in school or in practical applications, but in the personal development. Kids aren't always really interested inherently in that, right?
Very true. Well, I came to be very interested in let me start over. I think when I was in high school, I had a deep love for philosophy and metaphysics, but I didn't know how to articulate that. I loved fantasy literature, but I also loved reading about things like quantum mechanics. I loved reading about the history of math, but I wasn't very good at math. And so I thought, well, I'm just weird, and I have these, kind of fringe interests, but they're not really important. And then later on, as I've kind of pursued education on my own, I realized that what I was really interested in was the foundations and the meaning, and we just talked about harmony, the harmony between all of these different disciplines. And in my own classes, I really try to speak to how does geometry relate to history? How does your favorite book, you say this kid loves The Lord of the Rings, is there astronomy in The Lord of the Rings? And it turns out it's all over the place. And then encouraging kids, even if they don't grasp geometry easily, to appreciate the beauty and the logic of it. So I take in my course, because we work through Euclid's elements over the course of a school year, we take pretty frequent breaks, and we'll stop doing the theoretical, logical stuff and then spend a lot of time with just like a compass and a ruler and teaching how to draw a perfect square or a perfect pentagon. And so some of the kids that don't grasp things as intellectually, as abstractly, really love when you just put tools in their hands and then they can see it worked out. And then some of the kids really love it when we stop. We spend a little bit of time reading an old British satirical book called Flatland. During, right before Christmas break every year, we stop Euclid and we read Flatland, which is a story about a civilization that lives all in a plane, and the main character is a square, and he's telling you in the three-dimensional world what life is like in his two-dimensional world. And a lot of the kids that might not be interested in kind of the cut and dry geometric axioms really love this in an imaginative telling of all of the same geometric ideas, but now they're presented in a really humorous way. So I wish that when I had been in school taking math classes, that my teachers had presented a history of math and some of the more fun and interesting parts of math, in addition to putting pressure on me to memorize formulas, so that I would have a context, which I didn't really get, and an enjoyment of the beauty of math as well as the practicality of it.
Yeah, I'm seeing I'm hearing a few different pieces there. So you have that abstract mental part, which is just the logic of it, the logic of Euclid's elements, the prepositions and the abstract manipulation. But then you're bringing in with the compass and the pencil and a string. You're bringing in some practical, hands-on, physical. You're bringing it into the physical world and giving them a practical tool and an activity to do, demonstrative of this. And then you're also giving the other part with the Flatland is an appeal to the imagination and fantasy and wonder. And then another piece is the context, the why. Instead of just having the what, giving a why, and that historical context is. I think I would have liked to have that historical context as well as just sort of where does this all come from? Because it's sort of presented as here's these rules that exist, sort of in a vacuum, or we know this stuff. Now you got to know it. But I think it's interesting to see here's how this stuff was found out, and here's how it developed through time and history into what we all know now, I think. So Yeah, I'm seeing like all those different pieces coming together in a holistic way to like really make math something like fun and exciting, or at least interesting, instead of just sort of a drag as it is for many
Yeah,
people.
because I always tell my kids, I say, look, I don't speak math, so this has been a struggle for me my whole life, but I've always loved math. It's like Spanish. I don't speak Spanish, but I love to hear Spanish spoken. I think it's a beautiful, sonorous language. And I want the kids in my class that don't immediately grasp geometry to still love it and be able to read about it and know what is being talked about when we're discussing some other maybe higher level math. At the end of the year, if I have time, I try to throw out in my classes things that I don't fully understand myself. Like we will read some Lobachevsky non-Euclidean geometry. We'll read some number theory, like Cantor and Dedekind. We'll even read a little bit of Einstein's special and general relativity, because there's a lot of geometry and some algebra in that. And we sit and we read these. There's no test on them. There's no sense that you have to understand this. And when that pressure's off, then a lot of the kids are like, hey, it's the end of the year. I took my geometry exam. Now I'm just going to look at what other crazy things are out there in the world of mathematics. And even the kids that really struggle with math, once it's just for fun and looking at all of the other possibilities out there, some of them just really come alive and have lots of great questions and insights that I would never have thought of myself because I don't speak math.
Yeah, that's like hitting on something that like learning is inherently fun, and kids like learning. Everybody loves learning, and the kids love to learn, and then it becomes something can become something that's a drag when it's like enforced or made to fit into this model of like testing and scores and like, or just sort of telling you something they have to know and then recite, and instead it's like, and there's sort of these ideas of like learning being inherently fun, and also the idea of having the practical physical tools like the compass. That reminds me of another like education philosophy of Montessori, which was like getting into kids' inherent desire to do and learn and love of learning, and making it appealing to that and being majorly different than like a sort of the system that is widespread now. And it's also interesting that you brought in relativity with Einstein's special and general relativity, because I think I've seen it argued that relativity gives like sort of can tie back into cosmological models of the world and show that like simultaneously different models can be true due to relativity. Like,
yes.
Do you know what I'm talking about?
Like, was Einstein a secret geocentrist? is the question that's posed occasionally.
That's interesting. Yeah, I think I haven't read this book, but there is like a Russian Pavel Florensky priest and scientist, and he wrote a book that said like Einstein's special relativity corroborates Dante's cosmological model. Like he argued for Dante's model being like true, accurate based on special relativity. It's my general understanding, but we'll leave that as an interesting rabbit hole for interested listeners to go down. Thank you so much for coming on the show. We just have 1 minute left, so everything you want to say before you go?
Well, thank you very much. I'm watching the sunrise right now. I'm sitting here with my cat in my lap, and this is a great way to spend a morning. So I really appreciate you having me on.
Oh, amazing. Yeah, that's so cozy with a nice cat and a sunrise. It doesn't get much better than that. So, yeah, thank you so much for coming on, and I really appreciate we talked about today about the Vernal Equinox and cosmology, the development of astronomy, and we moved that into classical education. This has been Sunrise Angels with DJ Leto on WUSB Stony Brook 90.1 FM. You can find the playlist for today's show at WUSB.FM with all the music I've played, and also a link to Joshua's course, The Art of Imitating Heaven, Structure, and Meaning in Ancient Cosmology, online, which, if you're interested in anything we talked about today, I'd definitely check that out.